Welcome back. In today's lecture, we'll talk about another topic called as the packet classification. And before we actually move into the content of course, so let's take a look at what exactly did we discuss in the previous classes. We said that routers need to do the primary job of the router. Any router in the internet network is to route the packets. Given a packet from any source to the network need to forward that to the corresponding destination, and the every router all along the path need to do this decision of where to forward that packet. That's the forwarding decision. And we said that there are millions of packets coming per second. The routers need to have the ability to forward those many number of the packets. So the internet or the routers, whatever the functionality that we discussed with a bunch of algorithms to provide that facility to do the lookup operation. So all of that was the best effort to packet delivery, meaning the network will do, or every router will try to do its best to deliver the packet to the correct destination. So that's how the internet routers have been designed to work, and it is not always guaranteed, that we know well. And in order to do the forwarding decisions, routers do consult the routing tables or the forwarding table or FIB information, and they pick up the destination IP address from the header field of a packet, and then do a lookup operation and forward that packet. But that is not the only, although routing or forwarding is the fundamental job of a router, but that is not the only thing the routers are supposed to do, or at least they are doing. So in addition to the forwarding decisions or constructing the routing tables, routers also do a lot of other jobs. So one of the other primary job any router in the internet does is something called as the differentiated service. What it means is, if let's say there are two people, let's say A is here and B is here, these are two computers, and I got a router. Let me call this router as R1, and there is a second router, R2. They are connected, and A and B are connected to this router R1, and there are two other computers X and Y which are connected to router R2. And what it means, differentiated service means is, so every time A and Y talk to each other, you provide a priority based service to these two endpoints. A and B will have the in the communication, while B and X or B and A each other, you will have a different priority assigned to that. So meaning, I can define in the network, or I can tell my routers in the network to do a kind of differentiated. So based on who is talking to whom, whether what kind of protocol is being used, whether they are directly connected to the same router, or based on so many other parameters, you can actually decide to do this differentiation. So that's been usually practiced, and the routers which are out there in the network, at least in today's work, understand how to do this differentiation. And that also means that you need a mechanism to tell the routers how to do this differentiation. So how do I specify, how do I tell my router that, for example, R1 need to understand who is, let's say A and Y are talking, when they are talking. So what to do when B and X are talking, what to do with A and B when A and B are talking. So this kind of the specific understanding is required. So packet classification is all about doing this kind of the differentiation using some mechanism. So we will try to understand in this lecture how do we actually think about what are the mechanism, what are the algorithms, what are the operations we need to implement inside the router to facilitate this kind of the differentiated operation. That is the agenda. So let's try to understand the big picture with this diagram. What we see in this, a bunch of router. Let me name them as this. Let me call this as R1 and R2, R3. Maybe this one as R4 and this one as R5. And you can see a bunch of computers connected to this. So it is not that only when A and B are talking to each other, or A and X, Y are talking to each other, you need to provide priority. There are a bunch of other things that you can tell your routers to do. So for example, when this point 10.10.10.2 communicates with 20.20.20.2, this computer, you may want this to be given some priority over the other one. That's one thing. Or maybe when 10.10.10.1 talks to 20.20.20.1, this kind of the communication, whether he starts or he starts, I don't want to allow this communication to happen. I might tell my routers in the network that you deny this communication. So all of the routers do in the have something called access control mechanism or access control list. You can, using that, you can specify who is not allowed to talk to whom, and so forth. Maybe when 10.10.3 talks to 30.20.20.1, and this can be, you allow this transmission to happen, but if the rate is greater than some quantity, let's say delta, you drop the packets. Up to delta you allow, but beyond the delta you don't allow. So when this communication happens, so when he is talking, maybe he is taking this direct route and then they are talking. So now R1, R2, R3 need to be aware of that. So when 10.10.1 is talking to 20.20.1, we don't want to allow them. Maybe this is actually going through R1, R4 and then R3 like this. So now different set of routers R1, R4 and R3 need to be aware of what communication is not allowed. And now if 10.3 and 3 is talking to 30.20.20.1, this is going to a different set of the routers. Now R1, R5 and R3 need to be aware of this kind of communication, and then it is allowed, but only up to certain threshold of delta. Delta may be packets per second or bytes per second, whatever the parameter you want to use. Using that, you need to remember what is the rate at which these two computers are communicating to each other. So these are the kind of the stuff that we want to do. So this kind of the differentiation is not new. Even earlier also networks people used to do this. So this we call or study under a generic terminology called as the quality of service. For a variety of reasons, why we want to give priority to two set of people, why we want to allow deny traffic from two computers. There may be a variety of reasons. Maybe these two computers are running an audio video communication in real time. If you suppress their traffic, then the utility of the end applications might come down. If you experience jerk in the audio communication, then that's not the useful conversation. Or there might be other reasons, or we know that X and Y people connected to the internet are just running some useless application, maybe playing an online game or something. Although this is an hypothetical example, don't no offensive mean for people who use the internet for playing the games. But possible, as a network service provider, I may decide what is useful, what is not useful, when to curtail or drop the communication, when to provide priority to the end users, or maybe just because these two end users are subscribed to a higher bandwidth, they are paying more money, then you want to provide more bandwidth to them. Now the question is, how do we actually tell this to the routers? How do the routers understand that what need to be done with this particular packet? So one of the, this is a picture of the IP version 4 header. So there is a field in the IPv version 4 header called as the differentiated service or DSCP. So this field is in how many 6 bits field. Depending upon the value set inside these 6 bit number 8 to 13, 6 bit field, and the remaining 2 bits of that particular byte from 8 to 15 indicates the ECN. ECN stands for explicit congestion control. So these 6 bits, depending upon whether they are all zeros to or combination, all of them can be 1. So I am just giving these are the possibilities. So 2 to the power of 6 possibilities. So using the values that is set, maybe if let's say my higher 3 order bits are 100 and then this is 01, and using this, what is the meaning, what kind of priority you need to give to this particular packet, I can tell the router. This is one way of letting the router know what to do with particular packet. But this was historically used by the routers, internet service providers, to tell the router, okay, this particular packet is going with the DSCP field set with these particular combination of the bits, and using that the router will understand what priority need to be given to this particular packet. But over a period of time, this become an inadequate mechanism to let the router know we want to do much more very sophisticated differentiation of the service. So how do I actually do or engineer this kind of the facility in the router? That is the question we will try to answer. What kind of the data structure and algorithms and mechanisms that we want to do that. So in a nutshell, differentiated service requirements, what is the quality of service requirement that I want to achieve in my network, can be summarized in these particular points. So one thing that I can do is, given a particular packet or some particular node X is transmitting, I want to do the admission control. What it means is, I either allow this particular packet from this particular node X or I deny. And this allow or deny can be dynamic, meaning it can be conditioned on how much of the traffic historically X has transmitted. So whether in the last 1 minute so many number of the X number of the bytes have been transmitted from that particular node, or it's less than X, or what is that. So it could be a combination of that. At a particular point of time, I may decide as a router whether to admit this traffic from this particular node or not, and at this moment I might deny and subsequently I might allow. So that kind of the fine grained control I want to build inside the router, that's called as the admission control at the time of the when the packet is originating from the sender itself. And the second thing, I want to provide some kind of the prioritized services to the some kinds. Maybe go back to the same example, A and B are connected to this router R1, R2, R3, and maybe I have 2 computers here, X and Y. When A and Y talks to each other, this is the path, this is the path taken. So I want to ensure that R1 reserves some amount of the resources. When I say resources, it could be the memory, it could be the other power, whatever is there. So I want to reserve the bandwidth. So let's say all of them has got uniform bandwidth, maybe some 10 units of the bandwidth. It might be Mbps, Gbps, or whatever you want to take. A fraction of that, out of 10, maybe 1 unit of the bandwidth is reserved between router R1 and R2, and another unit of the resource is reserved from the R2 to R3 and so forth. So 1 unit all along the path, 1 unit of the bandwidth, whether it is Mbps or Gbps. So let's say Mbps, 1 Mbps bandwidth is reserved for exclusively for the communication between A and Y. Now the router need to be aware this bandwidth has been reserved for such a purpose, whatever might be the end use cases. But I want to do this. So if you want to do this, how do I do this? And third thing that I can do is, I can do, so we from the previous discussion, if you recollect, every router has got a queue, and every time a packet, let's say the queue of this router R1 is looking something like this. Every time E sends a packet, the packet would come from that on this particular link, and it will come and sit in this queue. And let's say B and X are also talking, the B's packet will also reach R1. So maybe his packets will also come and sit here, and so forth, depending upon the rate at which A and B are transmitting. The packets will come and accumulate inside this queue, and then you need to do the lookup operation and then forward these packets. So now instead of doing this, having one common queue for all the flows, that are all the communications which are flowing through this particular router R1, what I can do is I can have two different queues, one for the communication involving these packets, and the second one for the communications with the involving with the host B. So all the A's packets originating from A will come and sit in this queue, and all the packets originating from the node B will come and sit in this queue. Now, if I want to do related agreement, I can give certain priority to people. Maybe A's and Y have got priority in communication. I can tell that this is highest priority queue, and the second one, this is the lower priority queue. So when I am going to pick up packets from this particular input queue and then doing an inspection route lookup and forwarding, I will say that first you pick up the packets from the higher priority queue and then do the lookup and do the forwarding. If there are no packets inside the higher priority queue, then I go to the lower priority queue and pick up the packets and then forward. So like that, it is not necessary that you have only two queues, but you can have as many number of queues as you want, and I can order them. This is the highest priority, next higher priority, next higher priority, and so forth. So I can decide, and depending upon how many number of the priorities or differentiated service I want to provide, I can have multiple number of the queues and then appropriately pick up the packets for the lookup operation and forward. And at the same time, if I do this, so let's say I say that I always look for the packets in the higher priority queue, and if there are none, then you come to the next higher priority queue and the next one, so forth. Then what can happen is, if A and Y, in this case, if we assume there are only two queues at this moment, if A and Y constantly pump packets to the network, and the router R1, the queue reserved for the communication involving A would be always full. There will be always packets. So then the other persons B and X will, although they want to communicate, they will not get any resource, or their packets will not be scheduled for transmission, for the lookup. Now we don't want that to happen. So indefinitely B and X need not wait in the network. Although I want to give some priority to A and Y, but at the same time I don't want B and X to suffer indefinitely. So that brings us to the question, how do I actually differentiate? How do I become fair to all the users? Although A and Y got the priority, but I don't want B and X to suffer either. So this is called fair scheduling. I will do the priority, but not at the expense of the other ongoing communications or other people who are involved or dependent on the resources in the network. So that is the practical decision. We at the same time, we want to do prioritize based lookup and forwarding, but at the same time I don't want others to suffer. How do I actually do this? So this actually you need to tell the routers something using something called as the flows. Whenever two endpoints communicate with each other, the series of packets that are exchanged are called as the flows, and these flows are evaluated using a set of rules that we call it as the classifier. So classifier is a collection of the rules. So for example, I might have a bunch of fields. Maybe I will use the source IP address and then the destination IP address. Whenever, let's say, the computer 10.1 is sending to another computer 20.1.1, so you allow this communication to happen. So this is a example of a rule. rule written with two fields. One is the source IP address and the second one is the destination IP address. And then what action need to be taken when this combination is matched is the action field. So I have bunch of fields to look for, and then at the end of this, if the rules are these conditions are met, then certain action you want to take, whether you allow, whether you deny, whether you prioritize, whatever you want to do, you tell that. So this is called collection of such kind of the rules is called as the classifier. Now you can imagine these fields whatever I have mentioned are coming from the header portion of the packet. I have got an incoming packet. So let's say A is the computer and there is a packet. Inside the packet contains two things. One is the header and then the second one portion is the payload or the actual content. So whatever the fields that I have mentioned here, the rules are written using the fields of the header. So now you can think of that is not only the network header, although these two fields source and destination IP address are coming from the network header, but there are other fields as well. So other headers as well, maybe the TCP header, the link layer header, whatever it is. So although purely technical in sense, the routing or the forwarding decision should not depend on the other fields, but practically the fields of the other headers are also used. So I can write a set of rules using a combination of these header fields. So an incoming packet arriving at the router, you pick up the header portion, the bits corresponding to the header, and then you extract the required fields from that header, and against a bunch of rules written inside the router, you match it and then you take the corresponding action. So here is an example of the how the classifier rules might look like. There are 4 rules in this table. This is a classifier. So classifier is usually denoted with the capital letter C, and it is a collection of these rules. So here in this case, rule R1, R2, R3 and R4. And there are 5 fields that are used here. These are also called as the dimensions. D1 is one field, D2 is the second field, D3, D4 and D5. So the first rule says whenever the source IP address is 10.10/16, this is the /16 address. Any computer which is sharing this common prefix 10.10 and going to the destination 20.20, again the prefix format /16 address for the entire series of 2 to the power of 16 combinations at the source and 2 to the power of 16 combinations on the destination field. If the protocol of the communication between these any two entities falling under this series, and the TCP and the source port is actually 5000 and the destination port is 181, you should not allow this communication to happen. So second rule says it is an entire 30.30.30.30 and the destination IP address is the class 16 address going to 20.20 and the protocol field is TCP and the source port can be anything. I don't mind, star indicates the wildcard entry, but the destination port number is 80, then you forward it to port number 3. This is the classifier for router number 3 in this diagram for this router number 3. So like this, it will not only have one rule but a bunch of rules. Similarly, R3 says that when 10.10.1 is communicating with 10.10.2, if the protocol is UDP, doesn't matter what is the source and destination IP address, you forward it to port number 2 but with a certain priority. That's what it says. And similarly R4. So now you can think of whether D1, D2, D3, D4, D5, these are the only dimensions that I can have. No, not necessarily. I can have as many number of the dimensions or the fields that I want to have. In nutshell, what I am trying to say is using a combination of the header fields, you can write some rules by looking at those rules, the router can dynamically decide what to do with this particular packet. So these collection of the rules is called as the classifier, and when a classifier is there inside the router and it is inspecting the packet header and doing this lookup operation and taking that action, that process is called as the classification, in precisely packet classification. Now the packet classification in action, how do we actually do this? So you can look into this particular set of the rules. The rule number R3 says that, rule number R4 says that drop the packets if the rate is greater than 10 Mbps, but up to 10 Mbps it is okay. Both this particular IP address and these two are, there is a typo here, maybe 20.20.20.1 is connected to or talking to 20.20.2. Now, if these two communications exceed this threshold limit of bandwidth utilization 10 Mbps, then you actually drop the packet. But in order to facilitate this, you need to remember the history information, meaning that how many number of the packets have been transmitted, how many number of the bytes have been transmitted. That history can be measured in terms of the packets, or they can be measured in terms of the number of the bytes, or it could be any other metric. So bytes per second, packets per second, packets per minute, bytes per minute, and so forth. Or I can even go to the granularity that if X and Y are talking to each other, how many number of the packets have gone in the forward direction from X to Y, and how many number of the packets have gone from Y to X. I can specify if the threshold number of the transmissions in the forward direction is greater than some delta, you drop it. If the utilization in the reverse direction is so and so forth, you do this action. So all kinds of the combinations are possible. So in order to do this immediate action, you need to remember the history. That requires something called as the bookkeeping work, meaning you need to, every time a packet goes from X to Y, how many number of the bytes have been transmitted this, you need to tell this. If my granularity is byte per second, and what time, how many number of the bytes have been transmitted in what packet. So the second packet, third packet, so let's say 100 have gone here, 200 in this packet, 300 in this packet, and if these three packets have gone in 1 second, then the total aggregate number of the transmission is 600 bytes, and in the last 1 minute. So using that, I want to make the decision whether the third, fourth packet that is coming from the same source going to the same destination, whether that should be allowed or not allowed, or should be sent with priority, not sent with priority, whatever action I want to take. So in a nutshell, what I am trying to say is the decisions are made using a set of rules, and each rule may require some kind of the bookkeeping work to be done by the router. It is not only one router. So all the routers in the network need to have one classifier. Every router in the network need to have a classifier, and every router need to do the bookkeeping work. So that's what. How do I actually, now you can see that lookup operation, we said that large millions of packets are coming, it need to do a quick lookup. Now we are bringing another thing which is saying I not only want to do the lookup operation, but also I want to do some kind of differentiation in the forwarding itself. That requires bookkeeping work for every two combination of the computers and the protocols and other field, whatever is there engaging in the conversation. That's actually a lot of work. Now the question is, how do we actually routers actually implement this kind of the feature? What kind of the things that you want to implement?